This is a Saturn 1B rocket. It was the predecessor to the Saturn V rocket, which took astronauts to the moon. In the first stage, it's powered by 8 H-1 Rocketdyne engines. These engines use 880,000 pounds of propellant in the first stage alone. The reason for the size of this large booster is shown in Tsiolkovsky's ideal rocket equation. The change in velocity is equal to the effective exhaust velocity times the natural log of the initial mass over the final mass of the rocket. This pretty much means the more mass you want to put into space, the more fuel you need to get it there. And when we add more fuel, that means you need more mass, which means you need more fuel, and you get a big rocket. Before we move forward, we're going to have to define a couple things: thrust and specific impulse. Thrust is the reaction force described by Newton's third law. Every action has an equal and opposite reaction.
This is the foundation of space travel. A rocket shoots propellants out one end, and it's thrown in the opposite direction.
Specific impulse is how engine efficiency is quantified. It's the thrust produced per unit rate of propellant consumption. Think of specific impulse as the miles per gallon your everyday car measures. The higher the specific impulse, the more efficient the rocket engine. Just as the higher miles per gallon your car gets, the farther you can go with the same amount of fuel. Chemical rockets such as the Saturn I are great for getting into Earth orbit because of their ability to produce a massive amount of thrust in a very short period of time. But they become very tough to manage in long missions because of their large fuel requirements and relatively low specific impulses. This is why researchers and engineers created the ion drive.
No, this isn't a fictional technology from your favorite sci-fi movie. In simple terms, the ion drive shoots extremely high-velocity xenon ions out the back of the spacecraft, giving it a very small push and return. Even though the thrust produced by these ions is tiny compared to chemical rockets, ion drives can run for months and even years without stopping because of their very high specific impulses. This allows ion drives to accelerate spacecraft to incredible speeds of around 200,000 miles an hour. Let's get into more details about how the ion drive works. To start, a cathode releases electrons into the ionization chamber where it then collides with xenon atoms, the propellant. When this collision occurs, one of the electrons from the xenon atom is knocked off, making it a positively charged ion. After the initial ionization process, the ions diffuse to the rear of the chamber where it then passes through two grids. The first grid is positively charged and the second grid is negatively charged. After the ions pass through the positive grid, they are then attracted to the negative grid, which accelerates them to exit velocities of up to 90 kilometers a second. After the ions are ejected, a second cathode is needed to release electrons out of the engine to return the ions to normal charge so they aren't attracted back toward your ship, which would cancel out the thrust. A power source is needed to provide electricity for the ionization process. Usually solar panels are used, but engineers have experimented with nuclear reactors to reduce energy loss as the spacecraft travels farther away from the sun.
In short, ion drives are praised for their ability to run for extremely long periods of time while consuming a fraction of the propellant that a chemical rocket depends on. This technology has the potential to send us farther than we've ever been before. Will we develop this technology to send humans to the moon, Mars, or beyond? Only time will tell.